Here we derive a one-sided decomposition of the Maar process itself. The idea is to rewrite the two-sided moving average as a sum of two one-sided processes, a past-only part, and a current future part. This is done by a partial fraction type identity that splits the product of the two inverse filters into two terms, each associated with one of the pure components. The resulting polynomials b1 and b2 have degrees strictly less than the original causal and non-causal orders, so this decomposition is parsimonious. Conceptually, yt is expressed as a linear combination of the pure causal component and the pure non-causal component, each transformed by a short lag polynomial. This decomposition is important because it prepares the mixture view of extremes developed later. In a large extreme episode, either the past-only part dominates or the current or future part dominates, and that dominance behaves like a Bernoulli selection. This is the EVT foundation behind interpreting some extremes as bubble continuation versus crash scenarios. This slide introduces a key structural step. We decompose a Maar-PQ process into two one-sided processes. The first component, y1t, is built only from past innovations, so it behaves like a standard causal object once you run time forward. The second component, y2t, is built from current and future innovations, so it is non-causal in calendar time. Each component has its own tail process when we condition on that component being extreme. The important punchline is determinism on one side only. For the past-only component, the normalized tail path is deterministic for negative maturities, while for the future-driven component, it is deterministic for positive maturities. So one-sided extremes are easy to predict in the direction where the component is driven. Y-Buan 1t is predictable in reverse time, Y2t is predictable forward. This sets up the mixture view of a global extreme episode as mostly past-driven or mostly future-driven. Here, we combine the two one-sided tail processes into the global tail process of yt. A crucial result is independence, the tail process associated with the past-only component and the tail process associated with the current future component are asymptotically independent. Then, the global extreme episode is selected by a Bernoulli switch ether, with probability proportional to the total A power mass of coefficients on the positive side. The extreme is generated by the past-only component, otherwise it is generated by the current future component. This is the EVT version of which side of the filter carries the dominant shock. Conditional on ether, the epicenter index n is inherited from the corresponding one-sided epicenter, and the whole normalized path is an independent copy of the relevant one-sided tail process. Economically, this Bernoulli selector is the first formal place where bubble-like versus crash-like branches can appear. Different sides of the moving average kernel dominate. Hence, different deterministic recursions govern the visible extreme trajectory. This slide states the mixture representation explicitly. The normalized tail process x or h can be written as ether times a copy of the first one-sided tail process plus 1 minus ether times a copy of the second. So extreme paths are literally mixtures of two deterministic families depending on which side dominates. The slide also clarifies a subtle but important point. These one-sided tail processes are not the same as the pure components, UH and VH, obtained by filtering the global tail process. The one-sided objects come from splitting the original process into past-only and future-only innovation sums, while U and V come from applying phi and psi to the extremal trajectory itself. Still, there is a link. X plus h can be reconstructed from UH and VH via the short polynomials b1 and b2 from the one-sided decomposition. In practice, that is what will later justify residual diagnostics. If one side is close to zero away from the switch, you are seeing one regime of the mixture in action. We now enter the first illustrative model, Maar ur 0.1, which is purely non-causal. The defining equation says today is linked to tomorrow through the non-causal coefficient psi, and stationarity holds for the absolute value of psi smaller than 1. If we iterate the equation forward, we obtain a forward moving average representation. Yt is a weighted sum of future innovations, epsilon t plus 1, epsilon t psu, and so on, with geometric weights psi to the power k. In the bilateral coefficient notation, this means that only negative index coefficients are non-zero and all positive index coefficients vanish. This is a clean benchmark because it produces a very asymmetric extreme episode. Extremes are generated by innovations located in the future relative to t, and the propagation is one-sided. It will therefore illustrate sharply how the epicenter index translates into a random truncation time for the future path of the spectral process. In terms of interpretation, conditioning on a large yt means we are effectively learning about one very large future innovation, and the model maps that future shock into today through the forward filter. This slide gives the epicenter distribution and the spectral tail process for Ma 0.1. Since only coefficients on the negative side exist, the epicenter n must be non-positive. The probability of a given k is geometric, with parameter driven by psi. Heavier tails, smaller a, and larger psi both increase the chance that the epicenter sits further away, i.e., that the dominant innovation occurs deeper in the future. The spectral process itself has a simple form. For maturities up to the cutoff h smaller than -n, the normalized shape follows a geometric curve psi to the power -h, while for h larger than -n, it collapses to 0. The interpretation is central. All trajectories share the same normalized past, -h, but the future is randomly truncated at the switch time h equals -n. So the only randomness in the shape is the random cutoff location, which is exactly the turning point logic in its simplest possible form. Notice that the switch event is literally the event the epicenter sits at n. So estimating where the truncation happens is equivalent to inferring the most likely epicenter location. This figure visualizes the previous description for psi equals 0.9 and tail index alpha equals 1.5. Each curve corresponds to a particular epicenter n, with its probability indicated in the legend. What you see is that for h smaller than 0, the trajectories coincide. The normalized path before the extreme date is pinned down by psi to the power -h, so the pre-peak buildup is deterministic. Differences appear only on the right side. After the extreme date, the path is abruptly truncated at h equals n, and beyond that point it is 0. The dashed vertical line marks this switch. When n equals 0, the truncation occurs immediately, so there is essentially no continuation after the peak. When n is more negative, the truncation happens later, producing a longer apparent bubble continuation before the collapse. The weights decline geometrically as n grows, so long continuations are possible but progressively less likely. This is the prototype of a bubble, a crash pattern, generated endogenously by a stationary heavy-tailed non-causal model. We now turn to the central example, Ma 1.1, which mixes a causal parameter phi and a non-causal parameter psi, both inside the unit circle for stationarity. The model links yt to its lag yt, 1 and its lead yt plus 1, so it can propagate a dominant shock on both sides of the extreme date. The slide provides the bilateral moving average coefficients in closed form. On the non-negative side they decay like powers of phi, and on the negative side they decay like powers of psi, up to a common scaling factor. This is extremely convenient for EVT because epicenter probabilities and spectral shapes become explicit. Conceptually, MEA 1.1 is the minimal mixed model where you can generate a deterministic-looking run-up and a deterministic-looking unwind, but with a random switch determining which side dominates and where the turning point occurs. The next slides spell out the epicenter distribution and the resulting spectral tail trajectories. This slide characterizes the epicenter index n and the spectral tail process for Ma 1.1. The epicenter has two geometric tails. For n larger or equal to 0, probabilities decay like phi to the power alpha n, while for n smaller than 0, they decay like psi to the power alpha, us n, with a normalizing factor that depends on phi psi to the power alpha. So the dominant shock can be either on the causal side, n larger or equal to 0, or the non-causal side, n smaller than 0, and the relative mass is driven by phi, psi, and the tail index alpha. Conditional on n, The spectral trajectory is piecewise geometric with a clear switch at h equals n. On one side, you follow powers of phi, on the other side powers of psi, multiplied to match continuously at the switch. In other words, the extreme episode is built by stitching together a causal geometric decay and a non-causal geometric decay, with the stitch point determined by the epicenter. This is the analytical source of bubble crash asymmetries in the mixed model. In forecasting terms, this implies that one-step ratios and returns inherit a discrete mixture structure, because the next step multiplier depends on whether n falls on one side or the other of the switch. This figure shows simulated spectral trajectories for MAR 101 with phi equals 0.8, psi equals 0.9, and alpha equals 1.5, for several epicenter values n and their probabilities. Unlike the MAR 0.1 case, both sides of the episode are active. Before and after the extreme date, the normalized path can grow or decay geometrically depending on which regime you are in. The dashed vertical lines indicate the switch locations h equals n. When n is negative, the switch lies to the right, so the left part of the trajectory is governed mainly by psi, and the right part transitions into phi dynamics. When n is positive, the switch lies to the left and the roles invert. The probabilities decrease as nmax increases, so extreme trajectories with very delayed switches exist, but are rarer. Visually, this produces a family of bubble-like paths, where the build-up and the unwinding slopes are controlled separately by psi and phi, exactly the mechanism we will exploit later for one-step forecasting in extremes. On this slide, we open the forecasting part of the paper. We want the conditional law of the spectral tail process one step ahead, given what we have observed around the extreme date. The motivation is simple. If today is extreme, then the ratio of tomorrow to today is governed by the one-step spectral coordinate. Call it x at horizon 1. So understanding that coordinate is the EVT analog of building a one-step predictive distribution in the extreme regime. The key idea from earlier slides is that the entire spectral path is indexed by the epicenter n, hence the one-step coordinate is a local ratio of two-sided MA coefficients around n. Therefore, conditional distributions reduce to an identification problem from the past spectral coordinates, which epicenters remain compatible, and what does that imply for the next ratio. In the next slides, we formalize this via coefficient recursions and a boundary event where branching can occur. One practical benefit is that this coordinate is scale-free, so the same logic applies whether the extreme is large or very large. Only the tail index governs how quickly the approximation kicks in. This slide fixes notation and states what we condition on. We observe an extreme at time t and look at a finite vector of past spectral coordinates over a window long enough to cover the MAR orders. For a MAR PQ, a natural choice is a window of length p plus q1 because the MA coefficients satisfy a recurrence of that order. The central message is that, once we condition on that past spectral block, the one-step ahead spectral coordinate can often be deduced almost deterministically. Why? Because the next coordinate is the next coefficient ratio in the same local neighborhood that generated the past block. So, unless two different epicenters generate exactly the same past block, the past identifies the epicenter and the next step is pinned down. The whole difficulty is therefore concentrated in aliasing cases where two epicenters yield the same past pattern. From an econometric perspective, this is the minimal conditioning set needed to mimic a Markov property for extremes. The next step depends only on a finite past block, not on the entire prehistory. This slide fixes the MAR 1.1 benchmark and rewrites it as a two-sided moving average. The model combines a causal parameter phi and a non-causal parameter psi, both strictly inside the unit circle, so the process is stationary even though it involves a lead term. In the bilateral MA form, coefficients are geometric on each side. For positive indices, they decay like powers of phi, and for negative indices like powers of psi, up to a common scale factor. This makes the spectral tail process explicit. The normalized shape at maturity, h, is the MA coefficient at h plus the epicenter index n, divided by the coefficient at n, where n locates the dominant shock. In particular, the past one-step spectral coordinate at h-1 takes only two values. It equals psi when the epicenter is on the non-causal side, n less or equal to 0, and it equals 1 over phi when the epicenter is on the causal side, n positive. Symmetrically, the next coordinate at h over 1 equals 1 over psi if n is strictly negative, and equals phi if n is non-negative. So, even before conditioning, the one-step extreme return is already a discrete mixture driven by which side hosts the epicenter. Here we characterize the epicenter distribution n for MAR 1 to 1. Because the MA coefficients are geometric on each side, the single big jump weights generate a distribution with two geometric tails. Probabilities decay like psi raised to alpha times the distance for negative indices, and like phi raised to alpha times the index for positive indices, with a normalizing constant k that depends on both tails. The slide lists useful aggregated probabilities: the probability that the epicenter is on the non-causal side, the probability it is strictly negative, and the boundary probability n equals 0. These quantities matter because the boundary event n equals 0 is exactly the switch configuration. It separates the case where the dominant innovation lies strictly in the future from the case where it sits at the interface. A convenient implication is the conditional split within the non-causal side. Given n is smaller or equal to 0, the probability of n smaller than 0 is psi to the power alpha, and the probability of n equals 0 is 1 minus that. This psi alpha term will reappear as the key mixture weight in the one-step conditional laws. This slide explains how the switch event n equals 0 drives the conditional law of the next spectral coordinate. The first point is a deterministic identity linking the h equals 1 coordinate to the h equals 1 coordinate, plus a correction term that is present only when the epicenter is exactly at 0. You do not need to read the displayed equation. The meaning is that away from the boundary, the next spectral step is determined by the previous one. But when the previous step equals psi, we only know that n is non-positive, and there are two possibilities. Either n is strictly negative, which implies the next step equals 1 over psi, or n equals 0, which implies the next step equals phi. Therefore, the conditional distribution of the h equals 1 coordinate, given the h equals 1 coordinate equals psi, is Bernoulli with two atoms, 1 over psi, phi. The weights come directly from the previous slide: probability psi to the power alpha for staying on 1 over psi, and 1 minus that for switching to phi. In contrast, when the h equals 1 coordinate equals 1 over phi, we necessarily have n positive, so the next step is degenerate at phi. Operationally, this means that the same observed past extreme shape can still imply two distinct next step scenarios, with explicit probabilities. We now translate the spectral result into a predictive statement for the observed one-step ratio Rt plus 1 equals Yt plus 1 divided by Yt in an extreme regime. The idea is that when Yt is very large and positive, the ratio Rt plus 1 behaves like the one-step spectral coordinate at h equals 1. The slide gives limiting conditional probabilities that are easy to interpret. If the current ratio Rat equals phi, that signals the epicenter is on the causal side, so the next ratio stays at phi with probability tending to 1. If instead Re equals 1 over psi, that signals we are on the non-causal side with n is smaller than 0, and then the next step branches with probability psi to the power alpha. The epicenter is strictly negative, so the process continues on the non-causal branch, and Rt plus 1 stays at 1 over psi. With probability 1 minus psi alpha, we are exactly at the boundary n equals 0, so the process switches and Rt plus 1 jumps to phi. In short, after a positive extreme, the next step ratio has a 2-point predictive law, and the branching probability is governed by psi alpha, tail thickness, and non-causal persistence jointly control continuation versus switch.